Okay, so these are the last four that have been requested. So let's take a look. So dilations, let's go through one through four. Um, so number one is a fairly long answer, but and I'm not going to go through the whole thing again because it's actually on the key, and I don't want to just rewrite it. But the whole point is, no matter how you can prove a dilation, it goes back to doing something that has something to do with a shortcut or the full definition. Like, and I'll give you a short example of what I mean. So we stated many times that you can take like the coordinates. As long as the coordinates are all multiplied by the same k factor, like x times k, y times k. In other words, all the vertices are multiplied by 2 or all multiplied by 3. You're going to have a guaranteed dilation, therefore similarity. But think about what that does. If I take a point and I move it, and I move all points the same way, what I'm actually guaranteeing is side similarity. And what I mean is, if you think about a side length being controlled by points, and I project this point by multiplying it by 3 in the x and y direction, that's going to move the side length along um, by the same k factor, but since the side lengths are controlled by the endpoints. So every shortcut we have has something to do with that. Like, so parallel lines, if you think about this, if all lines maintain parallelism, what you're actually meaning is angle-angle similarity. Parallel lines maintain congruent angles, therefore parallel lines for the image and pre-image would be angle-angle similarity because all the angles are guaranteed to be the same. Same as kind of in a lesser sense, it's true for like the alignment of the um, pre-image and image line back to the origin. That has a lot to do with both the side lengths and the angles. Like, so if those aren't aligning correctly, certainly you can't guarantee side lengths are scaling properly or angles. So without going into more detail, like, so just know that there's a connection. So here's the meat of it. So consider this figure with these vertices, and I consider image with these other vertices. Explain how you know whether or not they are similar, and they are constructed similarity statement. So what I'm really trying to decide is, well, how am I going to prove a dilation? Dilations are going to give me similarity. So what I really need to decide is has it been dilated or not. And I think what I'm going to do is actually just use this definition of dilation. I'm just going to check to see if the vertices will all multiply by the same number. The easiest way to do that is to simply line up the vertices. And I don't mean like on a graph, I mean just so I can work with them. So that's 2, 0. B is 3, negative 2. C is 8, comma, negative, so positive 10. Looks like garbage. Okay, 8, comma, 10. And D is 0, comma, 4. So let's compare to these other vertices. Let's see, E is 16, comma, 0. F is 24, comma, 16, negative 16, excuse me. G is 64, 80. And I'm just pointing those right for the problem. Um, E, F, G. It looks like D was mislabeled. E, F, G, maybe put an H in there. It should be 0, comma 32, all right? So what I'm going to try and decide is if this rule actually fits. Like, so if I look at my original image vertice, I'm going to check if they x and y have both been multiplied by the same number. And in this case, 2 times 8 is 16. 0 times 8 is still 0, so that works. Okay, 3 times 8 is 24. Negative 2 times 8 is negative 16. 8 times 8 is 64. 10 times 8 is 80. 0 times 8 is 0. 4 times 8 is 32. So this is going to actually work out. So this is going to work. And for the similarity statement, of course, let's just write out the vertices. A, B, C, D is similar to E, F, G, H that I adjusted it with K equals, in this case, 8. Right? So check the vertices, basically just using a definition. Right? So here we have ABCD is similar to DEF with K equals a third. And I have all these vertices. I want to know the new coordinates. So again, we're going to follow the rule. If I have a coordinate, the new coordinate, the image coordinate will be K times the X, K times the Y. Okay? And the K in this case is a third. So if I had A, which is 9 comma 0, that's going to take itself to D, which reduced by a third should be 3 comma 0. B, which was at 30 comma 12, now becomes E, reduced by a third to 10 comma 4. And finally, C, negative 6 comma negative 21, reduced by 3 one more time, multiplied by a third, of course. So it'll be negative 2 comma negative 7, right? Last one, we have the use analyze graph below, explain how you know whether or not the triangles are similar, and blah, blah, blah. Okay, so we could do this a lot of different ways. I think maybe the easiest way is just look at coordinates. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. So 6 comma 8. And then look at B, looking at, see, 3 comma 4. So right away, this tells me if this is indeed similar, this matches all of them. It seems to me the K factor here, since we're going from big to small, should be looks like half. Okay. So if I look at C coordinates, one, two, three, four. Wait, one, two, 7. So 4 comma 7. If I think about k being 1/2, it should end up at 2 comma 3.5. No, that's not right. Oh, it's 3 comma 7. 3 comma 7. I can't count. So it should end up, if I look at half, at 1.5 comma 3.5. So 1.5 comma 1, 2, 3.5. It does fit. And of course, in this case, they should all be negatives. I missed that. I'm sorry. Last one. Let's go out to A. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 2. Negative 9, 2. If k factor here holds of 1/2, it should be negative 4.5, 1. 1, 2, 3, 4.5, comma 1. Okay, so we definitely have a k factor, or so we definitely have similarity because I checked all the vertices and k factor is 1, so we can definitely claim that triangle ABC is similar to triangle A prime, B prime, C prime, with k equals half. Half implies we're getting smaller, not bigger. And if we look at the, the shapes, we are indeed shrinking, we're reducing. All right, guys, that's it. Good luck.